Air quality monitoring using remote sensing and GIS techniques. Air quality is a critical determinant of public health, ecosystem stability, and overall quality of life. Poor air quality contributes to respiratory illnesses, cardiovascular diseases, and environmental degradation, affecting millions of people worldwide. With rapid urbanization, industrialization, and climate change, traditional air quality monitoring methods, primarily relying on ground-based sensors, face challenges in coverage, frequency, and cost. Remote sensing and geographic information systems, GIS, offer transformative approaches, enabling large-scale, continuous, and cost-effective monitoring of atmospheric pollutants. By integrating satellite imagery, ground sensor data, and spatial analysis techniques, researchers and policymakers can gain actionable insights into air pollution dynamics, identify hotspots, and implement evidence-based interventions. Why remote sensing and GIS are transformative? Conventional air quality monitoring relies on fixed monitoring stations that provide precise readings but are spatially limited, expensive to maintain, and often unable to capture real-time fluctuations across large regions. Remote sensing and GIS overcome these limitations by leveraging satellite-based observations, airborne sensors, and spatial modeling. These technologies allow for the continuous mapping of pollutants such as nitrogen dioxide, sulfur dioxide, particulate matter, and ozone over large geographic areas. Moreover, GIS facilitates the integration of diverse datasets, enabling multi-temporal analysis, pollution trend detection, and predictive modeling. This combination transforms air quality monitoring from isolated point measurements to a dynamic, spatially informed system. Core tools and techniques. A variety of tools and technologies underpin modern air quality monitoring. Remote sensing satellites. Platforms such as Sentinel-5P MODIS and Landsat provide high-resolution imagery and atmospheric data. These satellites capture information on aerosol optical depth, trace gases, and surface reflectance, crucial for assessing air pollution. GIS platforms. Software like ArcGIS, QGIS, and Google Earth Engine enables spatial analysis, visualization, and integration of multiple datasets, including satellite imagery, meteorological data, and ground-based sensor measurements. Data analysis and modeling. Python and R libraries such as Pandas, GeoPandas, Rasterio, Scikit-learn, and TensorFlow allow for processing large datasets. Statistical analysis, machine learning, and predictive modeling. Visualization tools. Interactive dashboards and mapping libraries such as Folium, Plotly, and Power BI help communicate air quality trends effectively to stakeholders. Typical workflow for air quality monitoring. A standard workflow combines remote sensing and GIS with analytical modeling. 1. Data acquisition. Collect satellite imagery, meteorological data, and ground-based sensor measurements. Automated scripts can download and pre-process these datasets for the study area. 2. Pre-processing. Perform radiometric and geometric corrections on satellite imagery, reproject spatial layers, mask irrelevant areas, and align datasets to a common coordinate system. 3. Data integration. Use GIS to overlay satellite data, sensor readings, land use, population density, and meteorological factors. Generate thematic layers such as pollution concentration maps, hotspot identification, and temporal trends. 4. Analysis and modeling. Apply statistical or machine learning models to identify pollutant sources, predict air quality indices, or assess correlations between environmental factors and pollutant levels. Visualization and reporting. Create interactive maps, time series plots, and dashboards to present results for research, public awareness, or policymaking purposes. Advantages of remote sensing and GIS. The integration of remote sensing and GIS in air quality monitoring offers numerous benefits. Spatial and temporal coverage. Enables monitoring over large regions and at frequent intervals, unlike stationary ground sensors. Efficiency and reproducibility. Automated data processing and analysis workflows reduce human error and allow results to be replicated across different regions or time periods. Data-driven decision support. Provides actionable insights for policymakers, urban planners, and environmental agencies to target interventions, plan mitigation strategies, and evaluate policies. Cost effectiveness. Reduces dependence on extensive ground-based sensor networks without sacrificing spatial resolution. Real-world applications and case studies. Remote sensing and GIS have been successfully applied worldwide to monitor air quality. In India, satellite data and GIS have been used to track PM2.5 hotspots across major cities, guiding urban planning and pollution control measures. In China, Sentinel-5P imagery is integrated with ground sensor networks to produce near real-time air quality maps for public alerts and health advisories. European agencies leverage Google Earth Engine and machine learning models to analyze seasonal variations in nitrogen monoxide 2 and ozone, supporting policy decisions on industrial emissions and traffic management. Getting started for beginners interested in air quality monitoring using remote sensing and GIS. Learn core tools such as QGIS or ArcGIS for spatial analysis and Google Earth Engine for satellite data processing. Familiarize yourself with Python libraries like Pandas, GeoPandas, Rasterio, and scikit-learn to handle datasets, automate workflows, and implement models. Explore open-source datasets from NASA, ESA, and other environmental agencies for practice and research projects. Participate in online communities, tutorials, and webinars to develop collaborative skills and stay updated on emerging techniques. In conclusion, air quality monitoring is entering a new era driven by remote sensing, GIS, and data analytics. These technologies transform traditional, labor-intensive monitoring into scalable, automated, and insightful systems that inform policy, safeguard public health, and enhance environmental sustainability. As urbanization and climate challenges intensify, leveraging these tools is not just advantageous, it is essential for resilient, data-driven air quality management.